Thank you very much. I want to thank the organizers for inviting me. It has been a great conference so far, so I really enjoy being in Paris and I enjoyed the talks. Really great. So I will speak about asymptotic properties of word maps. So I will cover a number of topics that are related to each other, but they are sort of themselves, topics in itself, I think. So, okay. And the first one that I want to speak about is Ervaire's conjecture. I will explain what that is and its relation to word maps. Then another conjecture by Michael Lawson. Okay, so we will come to that. And then I will focus a little bit on word maps that have a trivial image in finite simple groups. We will cover some interesting case where we can say something new. Then I will go to the case of compact Lie groups. I will say something about generation of compact Lie groups and give you some applications to the theory of von Neumann algebras. So to the structure of unitary groups in 2-1 factors. So that's towards the end. So I hope we will get there. So that's the rough outline. And so various of these results are a result of collaboration with various people, with Philipp Dowerk and Abdul El-Kasapi. They are PhD students, or were PhD students in Leipzig, and Anton Klyachko from Moscow and Gady Kozma from the Weizmann Institute. Okay, so let me start. So let me explain the Ervaire's conjecture. So that's the following. So you start out with a group gamma. You give yourself finitely many constants, so finitely many elements in the group, and some integers, epsilon 1 through epsilon n. And then we say that this expression w of t, which is defined to be that right-hand side, has a solution in gamma, right? That's so what does it mean to have a solution in gamma? Well, it means exactly that you have some element in gamma that solves this equation. So if you insert h for t and you compute what you get, then you're supposed to get the neutral element. Then it's said to solve the equation. And so the question whether there is a solution in the group, so if it's a discrete group, it's typically a very complicated question. So we have a talk about, so Cyril Sellar explained what the theory for the free group already is very, very complicated. And for general groups, it's even more complicated, right? So in general, there will be no solution in gamma. But what Ervaire studied is the question whether maybe one can extend the group so that there will be some solution in this bigger group, right? That's, of course, a much weaker requirement. So we say in this case that there is a solution over the group gamma. So just in the case, you think of the case of fields, right, and the polynomial equation. So typically there will be no solution in the field, but you can extend the field and you find a solution in the field extension. So here you ask for the same thing, but in the category of groups and a suitable notion of equation. Right, so there are a few observations that are, oops, I run into the same problem. Okay. There are a few observations which are not so complicated, right? You cannot solve all equations over gamma, right? So for example, that equation, you can only solve it if A and B have the same order in gamma, right? Otherwise, there's no chance to find an element, even in the bigger group, that will conjugate one element to the other. Right, so that's clear. So there are some constraints on the equations that you can solve in bigger groups. And they are related to torsion. So maybe you have the feeling that it's about different types of torsion. But in fact, well, I get to this. Okay. One kind of torsion is enough. If you have a little more complicated equation, then you cannot solve it over the group. But I mean, definitely torsion is one of the problems. And if you look at the equations, then you realize one other problem that might be the reason for that is that the sum of exponents of your unknown variable that adds up to 0, right? So that's somehow we consider this to be something singular. And in fact, so that can be turned into a definition. You say that an equation like that is non-singular if the sum of these exponents, the sum of these epsilon i's, adds up to some non-zero number, right? So then it's called a non-singular equation. And so one way to formulate, well, I think this is not so good. So one way to formulate the conjecture is that, well, if this equation is non-singular, then it in fact has a solution in some group extension, right? So there's no counterexample to that. And it's kind of very complicated to approach because like in the algebraic case of fields, you can just write down the field extension that solves your polynomial equation. Here, You can also write down some cube that is supposed to solve your equation, but the problem is that that might be the trivial cube, right? So nobody says you that it's really a cube that contains your cube of coefficient. It might only receive a map from that cube, right? So if you write down the obvious candidate for a solution, it might be might not contain gamma as a subgroup, right? So the most significant result in that generality is a result that was already proved in the 60s. Okay. It's a result by Gerstenhaber and Rothaus, and they studied a topological cube, but, well, this does not refer to topology at all, but they made use of the topology, and they were proving that if you are inside the unitary cube on a finite dimensional Hilbert space, then actually any non-singular equation can be solved in UN itself. Right? So, and in particular, if your cube gamma is contained in UN, then any equation in gamma can now be solved over gamma because you can solve it in this bigger cube. Okay, so that's really resembling the fact that the complex numbers are algebraically closed, right? So that also has a proof using the topology, and here, in fact, we will give some proof. I will actually prove that for you in 4 lines, which is really analogous to this topological proof that the complex numbers are algebraically closed. So it's really a cool proof, I think. And so because you turn that really into a problem about continuous maps between, well, in fact, manifolds, so you consider this really as a continuous function, right? You insert T, a unitary, and you receive some unitary, and that's the map. It's a continuous map. And so, well, continuous map, you can consider that up to homotopy. Well, I get, okay. And so since the unitary cube is connected, you can continuously move all the constants to the neutral element, and you see that this map is actually homotopic to the map that just raises T to some power. And then already Hopf computed that this map has a non-trivial degree as a map between topological manifolds, and hence the other map also must have had the same degree, and it's non-zero, so this map must be surjective. And if it's surjective, then you can take any, well, pre-image of the neutral element, and that will be a solution to your equation. So that's the proof. It's beautiful. It's not combinatorial at all, and in fact, for many of these cubes, in fact, I mean, in that generality, there's no combinatorial proof of that statement. So it really uses degree theory and some sort of like some fixed point property. You can, well, formulate it also in that way. So that's
any compact group would do, right?
Well, I mean, you see what you need, and that's what you need. So it's exactly. Okay, so we would like to generalize this, or first of all, we would like to really exploit this result. And so first of all, having that property that you can solve all non-singular equations, so let's give that a name. Let's call it algebraically closed. Okay, so UN is a cube which is algebraically closed in this setting. And, well, it's, It's easy to see that, well, if you have algebraically closed cubes, then if you form a product of those, they are again algebraically closed, because you can solve your equation like coordinate-wise. And if you take a quotient of an algebraically closed cube, that's also algebraically closed, because you can lift your equation, solve it upstairs, and map the solution down. So it's really triviality. So, but that has a really interesting consequence, because it means that if you have some cube gamma that embeds into some abstract quotient of the infinite product of UNs, okay, so let's parse this. So this is the abstract, I mean, this is the infinite product. It's not, I mean, it has really interesting quotient. So you take some abstract quotient. So if gamma embeds in such an abstract quotient, then it satisfies this Ervaire conjecture. Right? And these cubes, they have a name. They are called hyperlinear cubes, and there's no cube which is known to be not hyperlinear. So it's implied if the cube is sophic, for example. There's no example of a non-sophic cube. So this approach, which was only using UN, really has the potential to prove it actually in the general case, right? Once we understand better which cubes exactly embed in such abstract quotients, and somehow maybe the most general question or situation that you could.
But the converse is not true?
No, I mean, no.
Does not satisfy the conjecture?
No. I mean, if it satisfies, I mean, if the conjecture is true, then maybe you can say that any cube embeds in some algebraically closed cube, but they don't need to be all of this form. So it's like this is. Yeah.
Correct conjecture is about solutions over, not in, right?
Mm-hmm. And so the question that I would like to state, because it's really, I mean, seems to be of some fundamental like nature in some sense, is any countable group actually the subgroup of an abstract quotient of a compact group? Right? Is that something that could have been asked, like, I don't know, maybe it has been asked 100 years ago, but I am not aware of any reference. Right? It would be really relevant if you could get also some structure on this compact group, because it would imply Cavers conjecture. And maybe it's not true, that would also be interesting, because most likely that would be an example of a group which fails to be Sophic or fails to have some, like, some other expected property.
Is there a Radulescu who introduced hyperlinearity?
I mean, he gave the name. I think he was the first to use that word. Many people have criticized that because it's, so in fact, it's a weak form of unitary. Someone should call it hypo-unitary. That's what Sorin Popper, in fact, suggested that. So, but it is, by now it's pretty common to have this notion. But to study groups that embed into the abstract quotients of this group, so that I think, I mean, Alan Kohn formulated this in the 70s already as a conjecture that this ought to be true for all groups, or I mean, even more generally for Neumann algebras of type 2-1.
Usually when people say hyperlinear, they mean one particular quotient. And you say any quotient.
Yeah, exactly. That's a little additional argument that there are, I mean, this of course has other quotients than the ultra products, but it's all equivalent. So as soon as it embeds in some quotient of this group, it's
so is your question just a question whether every group is hyperlinear, or?
No, this is the weakest form, the weakest question that you can ask, right? It's so. I mean, not all compact groups are of that type. I mean, they all embed in there, but having a normal subgroup is an additional condition.
You don't impose any condition other than embedding, right?
Sorry? Yeah, it's just an algebraic embedding. Yeah. So, and the abstract quotient, I mean, it will not be topological in the interesting cases, right? It really is an abstract quotient. Okay. Okay, so that's basically the state of the art. So far I mean, it's nothing new. So this observation here is due to Pestov. It's basically a side remark in his survey on Sophic groups or on hyperlinear groups. But I think it's really a fundamental observation, and I mean, the proof is basically this proposition. So, okay, but let's now get to a more general conclusions that you could make if any group would embed here, or if any group would be hyperlinear. So what I want to discuss now is equations in many variables, right? And so in an equation before, it was like some product of constants and one variable t. So if we have many variables, then an equation is naturally an element in the free product of gamma with the free group on n generators. Then you have n variables, and this has a natural augmentation which will play the role of the total degree. And so you call an equation non-singular if this augmentation will give you something which is not the neutral element, right? So that's the natural generalization to one equation and many variables. And our conjecture, that's a conjecture that we made with Anton Klyachko, is actually also in that case, if it's non-singular, there should be some solution over gamma. And we made some progress. If you assume a little bit more about this augmentation of your equation, and you also assume that this group has this nice embedding property, then it's actually true. And that already covers, I mean, non-trivial cases, because this could be, for example, the commutator of the two generators of your group, and then you could not reduce it to the previous case because the total degrees in either of the two variables are 0, right? So this is really a non-trivial situation that you cannot reduce to the previous case. And so the strategy is exactly the same. So we use this fact that such groups embed into unitary groups. So we adapt this strategy. And what we really prove, so that's like the replacement of this argument with the degree theory, is that if P is a prime and you have some equation with coefficients in the special unitary group over a p-dimensional Hilbert space, and your word, the augmentation satisfies some more refined condition, then you can actually solve this equation in SUP, right? So that's now, again, a statement that looks like you need to prove it with algebraic topology. And in fact, so I can tell you, I can give you the statement that, one statement that we are using. Proof is fairly complicated using mod P homotopy theory, but one case where you see where things enter is this computation of the cohomology ring of PUP, the projective unitary group. So it's this ring, it's a polynomial, truncated polynomial ring, tensor product with some exterior algebra. You have this co-multiplication which encodes the behavior of multiplication in the group on the level of cohomology. And the important observation that one can make, and that's the only thing I want to stress, is that this is a non-co-commutative Hopf algebra. So it has some chances to detect the effect of the commutator map, right? So that's maybe the only thing that I want to say. And so if you really look at PUP in the mod P homotopy theory, then you see such fine effects on the level of cohomology, and you can use that to prove that basically the corresponding map must be surjective, and hence again you find some solution as exactly in the argument by Gerstenhaber and Rothaus. Okay, so I will not discuss this any further, and instead, come to the next point, which is that actually already without any constants from the group, the previous questions are actually interesting and have been studied. So Michael Larson has made a conjecture, which one case which I will concentrate on is the following: you have some word in the free group, so let's say it's non-trivial. Then there should be some number which is capital N depending on the word, so that if N is bigger than this number, then the corresponding word map is surjective. So that's very in close analogy to the things that Aner Shalev presented, only that in principle the Lie group case should be much simpler than the case of finite simple groups, right? Because you have Lie theoretic methods and analysis and algebraic topology available to study this case, right? But only very little is known, and so as far as I know, that's sort of the only positive case which is really known. That's this joint work with this PhD student, which says that if this word W is not too deep in the derived series, and there are some arithmetic condition, then actually this is true, and this map is always surjection, right? So this map given by evaluating the word, right? So this word map. And so in particular, that's a case that people like to study. These angle words, which were recently also better understood in the case of finite simple groups, they are always surjective on PUN, right? So words of this form are always surjective. Okay, so I will not explain the proof. I just wanted to mention this result because I think this conjecture is really very natural, and so I wanted to report about some progress on that conjecture. So that was basically about, the things that I wanted to say about words in the free group, where we want to prove that under certain circumstances, the image of this word map is large, right? Either with coefficients in order to solve some equations, or without coefficients to, for example, prove this conjecture of Michael Larson. So the next aspect that I want to discuss is that even though the image tends to be large in many cases, it also tends to be small in other cases if you reverse the quantifiers in the right form. And so let me first discuss this for finite groups where it's basically obvious, and later also come to the Lie group case where I will be interested in words having a very small image and how short they can be depending on how small I want the image. So for finite groups, so for example for symmetric groups, well, the image can be as small as the trivial element itself, right? And in that case, a word is called a law, right? We have seen, we have heard talks about identities in groups. So that's just a different name for that. So that's a very simple identity. A word is called a law if it's satisfied by all pairs of elements in G, right? So, and what I want to discuss in the next minutes is what are the laws for the symmetric group and how short can they be, right? So the symmetric group acting on n elements. What are the laws for the symmetric group? Well, there's one that we immediately see. Well, a to the n factorial, that's a law, right? That's fairly long. We want to do better than that. And if you understand why this is a law, then if you study the cycle structure a little closer, then you immediately realize that it's enough that you take the least common multiple of the numbers from 1 to n, right? That will certainly kill each individual cycle, and then it kills the entire permutation. This grows roughly like e to the n, this number. And in fact, there was a question in the Korovka notebook problem by Bokopolsky asking whether this is the best possible that you can do, no matter that you only used one letter so far, right? Even using 2 letters, he conjectured that you cannot do better than e to the n. This was disproved by Bu, Rabi, and McReynolds. They proved that there are words which have that length. And our theorem that I state here is that you can actually do much, much better. Right? This is still of the form e to the square root n. So it grows, well, it grows like e to the square root n. Whereas this is really e to the log n to the 4. Right? So it's much, much smaller. So it's really substantial improvement, in particular in view of that conjecture that was there in the beginning. And we can do even better assuming a conjecture. So assuming Babai's conjecture on the diameter of the symmetric group, so as the Gady graph for some generating set, we can even prove an upper bound or prove the existence of laws which are only in some sense polynomial, right? Log n, so it's n to the, so essentially it's a polynomial, right? And that's, I think, really surprising. At least to me it was really surprising because I expected it to be very, very complicated to construct a law for the symmetric group. For all permutations you have to be trivial, and there are so many permutations, right? And factorial permutations, in the end this word is much shorter, and so I thought that is a surprise.
Is there a trivial lower bound on the left?
Yeah, that's a very interesting question. So the only non-trivial lower bound is 2n. Right, so I have not seen an argument, a complete argument, let's say, for 3n. That's really surprising because for sure there will not be a law of such a short length, right? But it's
W in your result.
Well, I will exactly prove this result in the next minutes.
And if you use so if you assume what is Helmholtz-Serres result, what do you get?
Well, we are assuming it. That's why we are getting exactly this form. Yeah. So I would have mentioned this in a second. So, no, I mean, if you know his work, then you will realize that there's something, some resemblance in this expression, and it's exactly that. So how do we prove that? So the strategy, if you construct laws for groups, is there's a well-established strategy by now, which is proving that you first find finitely many words that somehow together behave like a law, right? So you want to start out with finitely many words, W1 through WK, so that for each pair there exists at least one of these words which trivialize it, right? So that's probably easier to construct, right? And you want to combine them, and that's exactly what the lemma does. Well, if you have that, then there exists one law that will now actually work for all pairs, and the length can be bounded by that expression. So it's essentially, well, the square of the number of words and then the maximum of the length of these words, right? So you basically parallelize this set of words. So the proof in the case k equal 4 is really simple. You essentially take this iterated commutator, right? Have to make sure that it's not trivial, but let's assume it's not trivial. Then you see that if at least one of these 4 words is trivial on some pair, then the whole thing will be trivial, right? And then you basically compute how long is that iterated commutator, and you will end up with such a formula. Right, so that's a mechanism that has been used by Martin Kasabov, and also I think it has been used before, definitely. Sorry? Uzi Haddad, okay. Okay, so that's the mechanism that we want to use. And let me make now one remark, because using this mechanism, we get now already a proof of this second, I mean the previously known best upper bound, which just relies on the following result of Landau. Landau, long time ago, proved that the order of an element in the symmetric group is at most e to the square root n, essentially. And that's due to the fact that you cannot have all cycles from length 1 to n, because that would need n square space. You only have n space, so you can only use a few cycles, and then he computed exactly how bad that can affect the order, and that's what he got. Right, so if we apply now the lemma to the words wi equal to a to the I, right, for I between 1 and this upper bound, then they will satisfy the assumptions, and so we get some word that it will be trivial always, which is only of the length 16 times the number of elements squared times the length, so that's all n, and so it's essentially the same number. So that's the proof, and that's actually a very easy construction that gives you already a sort of well, smaller bound than the exponential bound that was conjectured to hold.
It's a good question, but this is a word on one variable, so what are you?
Yeah, exactly. So so this really uses that you have f2, because if they are commuting, you first have to conjugate one of the two and then take the commutator. So you need this second letter to make this resulting word non-trivial.
So you use LVI to be sometimes AI and sometimes BI, or what?
No, as I said, I'm using a1, let's say, and here I'm using a conjugate of a square.
Oh, okay.
Namely, and then they don't commute, and then everything is fine. That's why you have this 16 here. So you need some adjustments.
On the previous slide, you were speaking about laws in how many variables?
I'm only studying laws in 2 variables, but it's not a big deal to. Okay, so now the aim of the proof to construct this better bound is really to provide a more clever set than just the consecutive powers from a to the 3 up to a to the capital N, and that's done using a rather deep result of Harald, Helfgott, and Scheres about the diameter of the symmetric group on an arbitrary, let's say, 2-element generating set for that purposes. Okay, so that's what we want to use. It relies on the classification of finite simple groups, and we will, in the course of the proof, what?
Unfortunately, that.
Well, I mean, in our case, we will use the classification again, so it wouldn't help if you can do it better.
To remove the classification from our proof, I don't think it's impossible, but it's an important problem. Well, for me, it's important.
Okay, so that's a bound on the diameter. Let's remember this. And now I can, on that slide, prove you this upper bound. So we take, that's the first step. We abbreviate this number by d. That already saves a lot of space. And then we realize, or we ask someone to tell us that if this is a group and the diameter of the random walk is d, right? So you reach the other end of the group after d steps, then d square log of the size of this group is actually enough for the random walk to mix on the group. Right? So if we have done that, then what we're trying to do with our random walk, we reach a set of elements that are easy to kill. So we try to reach the set of n cycles. Right? And sorry?
Shouldn't it be log n to the 4th?
Here, yes, yeah, should be log n to the 4th. Yeah, okay, but yeah, that's right. So we try to reach a set of n cycles. There are in proportion 1 over n cycles in the symmetric group. So the mixing time is defined in such a way that after that many steps you have reached this set at least with probability 1 divided by 2n. Right? So less, but still big. And what we are now doing, so now you have to somehow follow me through the next steps here. We take n cubed independent instances of this random walk after that many steps. And, well, we want to understand, first of all, what is the probability that at least one of these instances will bring us into the set of n cycles. Okay, so one of the things will end up in the n cycles with probability 1 divided by 2n, so it will not end there with 1 minus 1 divided by 2n. Now this, since this is independent, will happen for all of these instances only with this very, very small probability, and so you at least once end there exactly with this probability. So the key is that this is really, really big, right? It's really very close to 1. In particular, it's bigger than this number, right? So it's very easy to estimate. So in particular, this probability, I mean, the mistake that we make for a particular a pair of starting points is smaller. I mean, the inverse of that is smaller than the number of possibilities to start, right? The number of possibilities to start is only, well, let's say n factorial squared, and that's even a number which is much smaller than this probability to fail, right? So what we conclude from that by just some very trivial union bound is that actually this will happen for one particular n cubed tuple for all generating pairs simultaneously. Right? Just because this number is much smaller here than the number of generating pairs. Right? So we apply the lemma. So we know already how to parallelize this phenomenon. We apply this lemma to the nth powers, right, which are all trivial because there are n cycles of these n cubed words, and we get a word that is trivial on all generating pairs. And it has length exactly like our formula predicts. It's 16 times the number squared times the length of the words, which is just the time we walked times n because we took the nth power. Okay, so that's again, because d is so big, it's again of exactly the same form. So why are we not done yet? Well, we are not done because we assumed that, I mean, we can only do that argument if the pair of group elements is generating. Right? If we have some other permutations that are not generating, then they might generate some crazy subgroup of the symmetric group. And the only way, I mean, we would like to do some inductive procedure to understand this problem. Maybe, I mean, it should be easier if it generates a smaller group. But unfortunately, we have at this point really to use the classification again to understand what are the possible subgroups, the possible maximal subgroups of the symmetric group that it could end up in, right? And so we have really to do a very careful induction process to also treat the non-generating pairs, but it will not make the bound any worse. Yes?
So it seems like you do not need the full space of barbaris conjecture. You just need what is required in step 2.
I mean, you need to reach the set of n cycles. You could.
But that's weaker.
That's weaker. Yes, you can. If you have a good understanding of what irreducible representations are needed to understand the n cycles, maybe you can get away with less than really a diameter bound. Unfortunately, we are not able. We looked at that, but we were not able to improve.
What kind of spectrum irreducible representation?
Well, you need some. I mean, the diameter implies a spectral gap on all irreducible representations, and we would only need the irreducible representations that are related to the characteristic function of the set of n cycles, right? So that's projects on, I mean, it's not projecting, but it's not all representations are involved in that, right? So, but we.
Are you positive that you do need classification to do 6?
Well, I mean, it could be. I mean, there are other cases. I mean, okay, I don't know. I mean, what does it mean to need it? Yeah. So
it's very similar to. I mean, Sheresh and I were annoyed that we couldn't avoid classification entirely. We just ended up using it once, and it was in a fairly similar way. But there has to be somebody who knows tricks to get around this.
This is like standard way. There is no way.
So.
Well, more here than Sheresh. Maybe it is not Sheresh. Maybe there was another way.
Your stuff is probably more important.
Okay, so maybe you discuss. I mean, I think we couldn't avoid it, but that's what that means. I leave you to judge. So that. Okay, so why did I actually start to study? I start to study the laws for the symmetric group. I was interested in a question which is more about topological group. I just want to mention it very quickly. The question is, so let me show you the entire slide. The question is, if you have the full group of the hyperfinite equivalence relation, which is essentially built out of symmetric groups in a very straightforward way, does it contain a discrete free subgroup? That was the question that I really like for quite a number of years now, and I cannot answer it. It seems fundamental in some sense. And if you have a sequence of very good laws for the symmetric group, then it should also provide you a way of proving that any subgroup cannot be free, any free subgroup, let's say, cannot be discrete, because it kind of converges to the identity. So far the bounds and our understanding is not good enough to prove that, but I think it's an interesting question itself. And even more could be true, it could be true that there is actually a fixed sequence that converges to the identity always if the group generated by these two elements is amenable, right? So that would be an even stronger statement that not only is any free group non-discrete, but it's actually the same sequence that would always converge to the identity as soon as you're inside some amenable ambient group. So one can prove that in a few cases, but these are not the interesting cases. So in particular, the full group of the hyperfinite equivalence relation is really some case that seems to be. And so that seems very natural in some sense, because it's not true that an amenable Polish group has the property that discrete subgroups must be amenable. But if you have a bi-invariant metric, so if you're a little closer to commutativity or a little closer, then it could be true, and it would be a very natural generalization of our intuitive thinking of amenability, that it passes to subgroups in some sense. And so under this additional condition could be true, and it would be, maybe there's a trivial proof because it's such a natural statement, but I couldn't find it so far.
So I think the answer to the first question is yes. The full group contains, it's misfitting. The full group contains a free subgroup.
Yeah, this is the full group often in the measurable setting.
I believe the answer is yes.
Yeah, but is it discrete in the topology coming from the full group as a topological group, right? Or even if it's countable, it might have a non-trivial topology in your setting. So yeah. Okay. So let's come back to how I started with the study of word maps on compact simple groups. So that's a result that I proved, and Anna Shalev mentioned that it also Elon Lindenstrauss proved it, that there's a word in the free group on two generators that will shrink everything to an epsilon neighborhood of the unitary group. So here, this is not contradicting Larson's conjecture, because you now fix n and you find a word, whereas in Larson's conjecture he had a word and he was making statements for all large n, right? So that's reversing the quantifiers and exactly gives you also completely opposite behavior. In fact, for any n, there are words which shrink very much. And I was interested in the question, how much can they actually shrink simultaneously all the unitaries depending on the length of these words? And so that's the latest bound which I want to present you. So you have the group UN, n is fixed. And so this asymptotics will not depend on n, in fact, in this statement at least. So there exists a sequence of words which are non-trivial, which shrink everything to the identity rather fast, given the fact that, it actually works for all unitaries at the same time. Right, so this question has been studied quite a bit for individual pairs of unitaries. How fast can you converge to the identity if you apply words of a particular length? So there are famous conjectures about that. I think even...
so it doesn't depend on n?
Well, the constant c depends on n. And it's also interesting how it depends on n, but I did not put it in the statement. So I wanted to fix n and only look at one un at a time. And so this is the best that we can get. And so it's an interesting question again that I cannot answer, whether this delta can actually be as close to 1 as you wish, right? Whether you can really simultaneously exponentially fast shrink the whole unitary group to a neighborhood of the identity. And that again is related to this previous question, whether there can be a discrete free subgroup in one of these amenable Polish groups. okay, so how do we get this behavior? How do we get this fast shrinking? So the mechanism is to take in a very efficient way iterated commutators, which are known to shrink neighborhoods very quickly. And so this leads to some other questions, which I briefly want to mention. So in some cubes, so we will study the free cube. So here I'm in fact taking the free cube already. Here I don't. So in the free cube, we have the lower central series, we have the derived series, and it's very natural to study the girth of these subcubes, which would be the minimal length of an element in the subcube, which is not the neutral element, right? So that's like the girth of the quotient Gady graph, right? You want to understand how that grows. And if you understand this, this will give you a good understanding of how quickly commutators can shrink neighborhoods in the unitary cube, because that's the only mechanism to shrink entire neighborhoods. Okay, in order to study these quantities, there are some asymptotics that one, is necessarily, led to study. So for example, this beta, it will grow exponentially. The alpha n will typically, will grow polynomially in some sense. And you have these two measures, how fast they grow, and it's not complicated to see that these are some real numbers between, the limits exist, and these are some real numbers between bit 1 and 2. In fact, this was studied by Malstein and Putman, not Putnan, but Putman, and they conjectured that alpha and hence beta is equal to 2. So that's not true. We will prove that they are much smaller. And so why is 2 natural? Well, if you look at derived series, for example, then a commutator, it brings you one step down in the derived series, and it multiplies the length of your word by 4, because a commutator has 4 sub-words. And so you would expect that maybe this should grow at most like 4 to the n, which exactly means that beta is equal to 2, right? And so what we prove is that we can do much better than 2. So these are these results with my students Kasapi. So we prove these bounds on alpha and on beta by an explicit construction. I will show you the construction. And so that's useful because this bound, this is exactly the inverse of this delta that appeared in the contraction of the unitary group, and the mechanism is already not so complicated. It's just exactly this observation that taking a commutator really brings you closer to the identity in a very efficient way, in a quadratic way. Okay, and so you don't have to, these numbers, I think they're insignificant. What is interesting really is that we have no lower bound for alpha, right? We would like to be able to show that alpha cannot be linear, that alpha of n cannot be linear. So our construction is very elementary. So we start with A and B in the free cube. We take this special choice of taking commutators, and I can tell you there are many other choices and they all don't work. So it's really important to do it in this exact way. And because if you do that, then there are two surprises that happen. And the first one is that this Bn is further down in the lower central series than you would previously expect. Right, so that's if you look at this formula, then you would expect there are some obvious implications how far down in the lower central series you are, but because of that formula, you are actually further down than you think. Right, so that's a little miracle that happens here in this situation. And another miracle is that we have set up our recursion so that there's really quite a lot of cancellation. If you iterate this, so the length of Bn is also shorter than you think it is, right? Because there's some cancellation. So how many minutes do I have, actually? 1 minute? Okay, I started a minute late. Okay, so let me just say, okay, we would like to prove that this is at least n to the delta for some n delta which is bigger than 1. And so, I think I will just stop here.
Because there are a lot of questions. So
okay. So this is well known that in the finite simple group, this was proven by Liebeck and Shalev, you can efficiently generate the group by a conjugacy class. And this is the obvious, the best possible thing that you could hope for, right? I will not explain this. And in the Lie group case, we basically prove the same thing, right? So we have some natural length function on un, and we prove that the simple Lie group PUN is generated by a conjugacy class, basically exactly as best possible permitted by this obstruction, right? That's our result. So there's a log which is not optimal, but this length obviously gives an obstruction to reach the other end of PUN, but if that obstruction is taken care of, then it's actually best possible. And this is, I think it's interesting in itself because matrices are interesting. And, but it has interesting analytic consequences because we can, using some careful approximation arguments, prove the same thing for a 2-1 factor. And this implies, the techniques that we are not using, not this exact result, but the techniques we are using implies these results. In particular, the second one, I think is very nice. These groups carry a unique Polish group topology, and they also have some automatic continuity property that follows from this kind of, from this interplay between algebra and topology that is somehow encoded in these relations. So I have not time to say anything about the proof. Let me just end with a picture. Sorry? No, this is for any finite factor for Neumann algebra. And this first one is even new if it's a type 1n factor. So, but let me still finish with this picture of Paris.
No questions?
I have a question.
Oh, please.
In the second to last slide, can you explain your notation?
Yeah, I was...
So the previous one. Yeah, what is the notation? In the last slide.
Here?
Yes.
Well, so U, this is the conjugacy class of U, and I'm asking how many factors do you need to cover PUN? And there are some, so without this factor, this would be obvious that you need at least that many steps. And so,
I didn't understand that. Okay, I see.
yeah, I didn't explain it, so sorry. I didn't understand the question. So,
so laws were defined as coming from free group of two generators, right?
yes.
So what about 3 and up? Did you look at that?
One can look at this. It's, from an abstract point of view, it's very natural to have all the identities. But if you are interested in these quantitative bounds, then you should only observe that the free group on 3 generators can be embedded in the free group on 2 generators in a very efficient way, and that reduces everything to the free group on 2 generators. Yeah.
Other questions?
A very brief question. You mentioned at some point that this was some connection with sophicity. Did I miss that slide, or did I miss it?
Well, in the beginning I said that if a group is sophic, then it is hyperlinear, then it would be an abstract quotient of a compact group.
The notion of hyperlinearity is older than that of sophicity.
Yeah.
Yeah.
Yes.
But other than that, there's no connection to sophicity that you're aware of? No.
And why dense subgroup of infinite dimensional unitary group is hyperlinear? You told that there is no unknown either such a group exists.
Yes.
And this group probably can be...
So a dense subgroup?
In infinite dimensional unitary group. Dense in group of all unitary operator infinite dimensional Hilbert space.
I think it's not known whether such a group is hyperlinear.
It's not known? Please?
I don't know whether this will improve bounds in any regime, but it might be useful for you to consider not just n cycles, but also elements that contain very long cycles, simply because a positive proportion of n elements do. So you reach them in a bit less time. probably not relevant when you just use my word differential, but it's maybe relevant. I said back of given on calculation you have to do when you assume Babai's conjecture. Maybe one can do it.
Yeah, exactly. So there was one point when so Babai's conjecture is that this diameter bound is polynomial, but still we are only getting n to the log n as a conclusion, and that there's some weak point in the argument which we don't know how to improve. But it's actually not this point, but it's this inductive step that I didn't mention at all. At this step, we are really you have to take care of so many cases that there is some more.
Yeah, in fact, I'm impressed that you get only one log, but at any rate, if it were not for that, you would get something polynomial now.
I mean, it's only the inductive step which makes us problems. Yeah.
Okay, thank you very much for letting me.